I'm not sure my brain is on, but we're going to go ahead and try Unit 2, Lesson 8, Comparing Shapes of Functions, and I'm giving you a break from the Stray Kids to prove that I can be obsessed with something else. Yes, I just barely discovered Stranger Things. So, they want to know, can you name each type of function? I'll give you a hint. This one right here is linear because it makes a line. See if you can figure out the others. This is a cubic, as in x raised to the power of 3. This is exponential. This is quadratic. Okay, this should be in your notes if it's not. Now, we have pages and pages and pages of review. I'm telling you right now, if there's one page at the end that I would recommend you put in your notes, and the rest of this is kind of long and boring and pointless. This is the page that needs to go in your notes. If you want to skip all of this stuff beforehand, go for it. Okay, a linear function is a function in the form of f of x is equal to mx plus b, where m is the slope and b is the y-intercept. Its graph is always a straight line. The most basic linear function, f of x is equal to x, is a line passing through the origin as shown. The domain of the function f of x is equal to x is the set of real numbers, and the range is also the set of real numbers, since the graph runs infinitely without bound in all directions. The graph has no minimum or maximum. It passes through the origin. Thus, the x-intercept is 0 and the y-intercept is also 0. Other linear functions can have different values for the slope and y-intercept, which are needed to write the equation of the function. A quadratic function is a function in the form f of x is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. The highest exponent of the variable x is 2. The graph of a quadratic function has the shape of a parabola. The most basic quadratic function is f of x is equal to x squared, and it's shown there in the graph. The graph f of x equals x squared continues infinitely to the left and right, thus its domain is the set of all real numbers. Since squaring a negative number results in a positive number, the graph never dips below the x-axis, thus the y values of the function do not include any negative values. The range, therefore, is the set of numbers greater than or equal to 0. The minimum value 0 occurs at x equals 0. The graph has no maximum value. The graph passes through the origin. Thus, its x-intercept is 0 and its y-intercept is also 0. Note that for other quadratic functions, the range, maximum, and minimum values and intercepts can change. This stuff only applies to the basic parent formula. An exponential function is a function in the form I didn't put it in the right place. Wow. It's f of x equals a times b to the power of x, where a is the initial value when x equals 0 and b is the multiplier. Its graph is shaped like a curve. An example of an exponential function is f of x is equal to 2 raised to the power of x, whose graph is shown. The shape of the graph of f of x is equal to a times b raised to the power of x, where b is greater than 1 is the same as that of f of x equals b raised to the power of x. Thus, the properties of f of x is equal to 2 times 2 raised to the power of x are true for any exponential function. F of x is equal to 2 raised to the power of x, where b is greater than 1. The domain is the set of all real numbers. Notice that the graph approaches but never touches the x-axis. Thus, the graph has a horizontal asymptote. That question is on your quick check, I believe, or your practice. The only graph that has an asymptote is an exponential one. The presence of the asymptote affects the range of the function. Since the graph never crosses the x-axis, its range is the set of numbers greater than 0. The graph has no maximum or minimum. It has a y-intercept at 0, 1, but has no x-intercept. A cubic function is a function in the form of f of x is equal to ax cubed plus bx squared plus cx plus d, where a, b, c, and d are real numbers and a does not equal 0. The highest exponent of the variable is x is 3. The graph of the most basic cubic function is shown. The domain and range of cubic functions is the set of all real numbers. The graph has no maximum or minimum. Like the basic linear and quadratic functions, the graph of f of x is equal to x cubed passes through the origin. Thus, its x-intercept is 0 and its y-intercept is also 0. Note that for other cubic functions, the range, maximum, and minimum values and intercepts can change. Okay, now this is the important one. All of that gobbledygook that we just went over is all laid out on this table. Put this table in your notes. It will answer almost all of your questions. The following table shows the key features of 4 functions: linear, quadratic, exponential, and cubic. Notice the ways in which these functions are similar to and different from each other. Now, if you vary from the standard formula for each of these, when you add, subtract, multiply, or divide components of these functions by a real number, it's going to change things, okay? It's not necessarily going to have the same x-intercept, y-intercept, whatever. But you can look here. Okay, so if the domain is the same for all 4 different types of functions, okay, that's one of the questions on the quick check or the practice. I can't remember which. This is important though. Pause it, write it. All right, here's a check-in. What key feature is shared between the graphs of linear, quadratic, exponential, and cubic functions? They all have the same domain, negative infinity and infinity, which is what I told you to write down right there. That was so important. This is on the end stuff that counts for a grade. Okay, example 1. Compare the shapes of the functions of f of x is equal to x plus 1 and g of x is equal to x cubed minus 1. How are they the same and how are they different? We'll go through this together. This whole lesson is basically just looking at graphs or tables and being able to interpret the information there. The function f of x is equal to x plus 1 is a linear function, and the function g of x is equal to x cubed minus 1 is a cubic function. Before graphing, create a table of values for each function. Plotting these points will give you the graphs. The book uses x equals negative 1, 0, 1, and 2. So we've done this quite a bit, but I will do a brief little review for you in case you don't remember. Basically, all you're going to do is you're going to take your x value, in this case, negative 2. So our first coordinate point is going to have an x value of negative 2. You're going to take your formula. So for f of x, we're going to do negative 2 plus 1 is going to give us our, this can also be traded out to y, okay? This is going to give us our y value, so y is equal to negative 2 plus 1, which equals negative 1. So our first coordinate point is negative 2, negative 1. This is for the f of x. And then to find the coordinate point for g of x, you're going to take the g of x formula, replace g of x with y, and replace the x with our x value, which our first one is negative 2. Make sure the negative goes inside that parenthesis. Cube that and subtract 1. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8. Negative 8 minus 1 is going to give you a negative 9. So your first point for g of x is going to be negative 2 and negative 9, okay? And I'm going to come over and show you this table. So this would be right here. So we have x is negative 2, then f of x is negative 1, and g of x is negative 9. And you would go down and fill it out for all of these. You don't have to right now. I'm just showing you how in case you need to. Okay, you can see I have the right information there. You go through and get all of your points. Then you'd graph these points. So negative 1, negative, oh wait, sorry, negative 2, negative 1 is 1 point on this blue line. And negative 2, negative 9 is a point on the orange line because we're dealing with 2 different functions. So this one is blue and this one's orange. And that makes sense because our f of x formula is a linear formula, so it's just straight. And our g of x is cubic, so it's going to be that little bend in it, okay? So now we can look at this and we're going to determine how they're the same and how they're different. If you go through, you can see that all of these points will line up to negative 1, 2, negative 9. Negative 1 and 0 is going to be right there, which is also on the blue line. -1 and -2 is going to be right there, which is also on the orange line. That was off, but you're used to me by now. So notice that both functions have the same domain and range of -infinity and infinity. Neither of them have endpoints. They both go on forever. Both of them also have no maximum or minimum. They go on forever. However, the function f of x has an x-intercept at -1, 0, right there, and a y-intercept at 0, 1. Okay, that's where it crosses both of those lines. While the function g of x has an x-intercept at 1, 0, and a y-intercept at 0, 1. They have completely different x and y intercepts. Okay, they do have a point where they both intersect, but it's not on the x and y axes. If you review the table again, you will notice that when the value of x is less than or equal to 1, so we're looking at here, okay, the y values of f of x, okay, these values right here, are greater than those of g of x. -1 is more than -9, 0 is more than 2, 1 is more than -1, okay? But when you get to x being equal to 2 and onwards, the y values of g of x are bigger than f of x, so it starts to get bigger over here, okay? This is where it flips. This is our magical, everything's going to change point. The graphs of the functions intersect at an x value between 1 and 2. So somewhere between 1 and 2, they're going to intersect, and if you follow it up, look, they do. Somewhere between 1 and 2, they intersect. When the value of x is less than the x coordinate at this point, then g of x has greater values. Okay? So sorry, when the x value is less than this point, then f of x has greater values. When the x value is greater than this point, then g of x has greater values. Okay? So blue is winning before they intersect, orange is winning after they intersect. Example 2, compare the shapes of the functions f of x is equal to x squared plus 2 and g of x is equal to 2 raised to the power of x. How are they the same and how are they different? We'll go through this together. The function f of x is a quadratic function because it has an x squared. And g of x is an exponential function because it's raised to the power of x. Okay. Start by creating a table of values to graph the functions. They do not ask you to fill out a table at the end. So here's all of your values, okay? I showed you how to do it if you needed to, but here's all of our nonsense, okay? You would take all of these and plug them in and get your 2 different graphs. You could also just plug the formulas into GeoGebra and save yourself a step, okay? So f of x is the blue line and g of x is the orange line, I believe. Yes, that makes sense. Okay. The functions have the same domain of -infinity and infinity. Okay. Domain is related to the x line, I believe. This is the way domain goes. The range of f of x is y is greater than or equal to 2. Okay. So when we hit this point, right there, that has to deal with range, which is up and down. And the range of g of x, which is this orange line, I believe, I can't really tell because it's so small, is greater than y equals 0. Okay. The y-intercept of the quadratic function occurs at 0, 2. There's the y-intercept for f of x. Okay. And the y-intercept of the exponential function occurs at 0, 1. You can see it's down here. Okay, so they don't intersect at the same place on the y-axis. Both functions have no maximum. The minimum of f of x is 2 when x equals 0. So when x equals 0, the minimum for this blue line is 2, which g of x has no minimum. Okay, because it just goes on forever. It has that horizontal asymptote. You may notice on the table that after x equals 5, this is going to be our point of change, okay, g of x begins to have greater y values than f of x. So up to this point, this is lower. It's actually between 4 and 5, but they're saying here, because here it switches. And then here, F is winning, 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 and then it's actually here, but they're saying at x equals 5. However, if you notice their graphs, you'll notice that the functions intersect at an x value between 4 and 5. So the table says right here, the graph says right here. Thus, g of x begins to have greater y values than f of x somewhere between 4 and 5, not exactly at 5. And you can see that here because they're close here, but they flip there. And you can see here, this is where they intersect, but it's going to be more in this area, more in between 4 and 5 than exactly at 5, okay? That's all that nonsense is saying. Here's a check-in of the different types of functions, linear, quadratic, exponential, or cubic. Which function's graph contains an asymptote? Do you remember? Exponential. I asked you that at the end, I believe. Question number 1, this one's all you. Between what values of x does the linear function f of x equals x plus 2 have greater y values than the exponential function g of x is equal to 2 raised to the power of x plus 1. So we can look here, we can see f of x is the blue. F of x is losing until we hit somewhere in here. And then it's winning a little bit, and then it starts losing again. So between what values of x does f of x win? I would say it's between about 0 and 1. Oh my, you were supposed to do that on your own. My bad. Hey, look, we were right. Okay. The graph of f of this, it's between 0 and 1. Okay, so you can just figure that out just by looking at it. Let's do it with a graph. This time I'm going to try not to just give you the answer. According to the table of values, at what x values does the quadratic function f of x have lower y values than the cubic function g of x? So when does g start winning? Pause the video and figure it out. Okay, I hope you paused. Let's see if we can figure this out. So right now, this is winning, this is winning, this is winning, this is winning. And all of a sudden, this is winning, this is winning, this is winning. So it's at this point that g of x starts to. When does f of x have lower values? It's between 1 and 2. Notice that from x equals -2 to x equals 2, the values of f of x are greater than the values of g of x, okay? And then, however, starting at x equals 3, they have all of these wrong in here. It's at x equals 2 that the values of f of x, that the values of g of x are greater than the values of f of x. This suggests that when the functions are graphed, the x-coordinate of the point of intersection between the two graphs will be between points 2 and 3. So they're saying right here. And I said a step higher. So I guess that's the thing. So I say they're changing right here, but you're not going to see the change until one step below, okay? When the x values are less than this x-coordinate, the quadratic function will have lesser y values than the cubic function. So this is the point, because sometimes it changes. So if I have a graph like this and I have nice big open spaces, sometimes they change right here in between. So we need to go a step higher. We're looking at this one. Even though the change happens between here and here, we're not going to really see the change until here. I hope that makes sense. Oh, that's beautiful. That says lorem ipsum dolor sit emet, which I have no idea what it means. It's a page I didn't delete. So this is practice question 1 at the end of the lesson. Do it now, write your answer down, and then you can fill it in later. Compare the functions f of x and g of x. At how many points do the functions intersect? Okay, we're trying to figure out how many times they cross. We saw earlier that sometimes they cross once, sometimes they cross more than once. Okay, here I am over on GeoGebra. I just created a table, put in my x values, my y values, and then my y2 values. I just automatically populated them with this. If I click on this, I can see that this is my first y1. This is an S curve. Okay, we don't have the formulas for these, but you can see that this is making the bend. Okay, so the line's coming like this, and our second formula is just a straight line. So it's going to cross just the once. Can you see that? Okay. This book never teaches you how to show that you know, how to figure out how many times it's crossing. But this, to me, very obviously says that it's going once, because it's all the same here, and then it goes up, and then it's all the same here, and it just continues on. So I would say once. So for this table, the functions intersect at 1 data point, or 3, depending on how you look at it, because it goes 1, 2, 3, that they all line up. You'll have to play around and see which one it accepts. Practice question number 2. Compare the functions f of x and g of x when is f of x greater than g of x? Okay, pause the video, figure it out, and then come back. So let's see. The winner here, they're tied. There's no winner here. Here is bigger, tied. Here is bigger, tied. Okay, so let's see. Tie, tie, tie. So when is this one winning? So I would say it's right here, but I was doing everything wrong, so I'm guessing this is going to be our line of division, of demarcation. I'm going to say f of x is greater than g of x when x is greater than -1 and less than 0. Let's try that, see if it works. I'm not being much help for you on this one. I'm sorry. Okay, the second half of the lesson. What are the domain and range for the function f of x is equal to the square root of x? We'll do this together. So this is what the model looks like. What do you notice? The input values of the square root function must be 0 or positive, because the function is not defined over negative values. It has an endpoint right here. It just stops. It doesn't go on over here. The output of the square root function does not have negative output values. So the domain is 0, infinity, or x is greater than or equal to 0, and the range is 0 and infinity, or y is greater than or equal to 0. This is probably in that original table that you should have written down. What are the domain and range of the function g of x is equal to the cube root of x? What do you notice? There is no limitation to the input values of the cube root function. It just keeps going. There's no endpoints. The output of the cube root function also has no limitations. So the domain and range are both negative and infinity, infinity. Okay. Example 3. How are the graphical representations of those two formulas the same, and how are the graphs different? So they put them on the same graph so you can look at them. On the same coordinate plane, what do you notice? F of x does not exist on the left-hand side of the graph. So f of x is orange. It just stops. On the right-hand side of the graph, g of x is greater than f of x between 0 and 1. So from here to here, g of x is winning. Okay, then they switch. At x equals 1, the graphs are equivalent and intersect. So there's our magic switch point. After the intersection at x equals 1, f of x is winning. It's greater than g of x. Both graphs are smooth curves. Each graph has the points 0, 0. They both touch there, and 1, 1. They both touch there. So here's question 1 that's for you. How are the graphical representations of f of x equals 2 times the square root of x and g of x is equal to 2 times the cube root of x the same? How are these the same? Pause it, figure it out, come back. Okay. So first, the graphs are similar in shape by starting at 0 and increasing quickly until x equals 1. Then becoming flatter, each graph shares the points 0, 0 and 1, 2. They intersect at those 2 points. We're only looking at how they're the same. Okay. Let's go on to question number 2. This one's all you. How are the graphical representations of f of x is equal to 2 times the square root of x and g of x is equal to 2 times the cube root of x different? This time we're looking at how they're different. Pause it, figure it out, come back. Okay, the graphs are different because the graph of f of x, which is the orange line, does not exist when x is less than 0. It just stops there. It has an endpoint, okay? In addition, the output values of the f of x function are greater than the cube root graph, so f of x is winning until x is greater than 1. And then G of x is winning until x is greater than 1, then f of x is winning. All right. This is at the end of the lesson, okay? Compare the following options and select the one that matches the graph. The graph of the function matches f of x is equal to the cube root of x, or the graph of the function matches f of x is equal to x, the square root of x. Pause it, figure it out, come back. It has to be this one, because if you come back here and look, when you have just a square root, the graph stops, okay? When you have a cube root, you get the full curve, okay? You get the point where it changes and it continues on. Practice question number 4. Select the option that matches the graph. This is either f of x is the cube root of x or f of x is the square root of x. Which is it? It's the opposite of what we did. This is just the square root because it has an end point. It stops. Okay? This is all because square roots cannot have a negative number under here. That does not work. But cube roots can have a negative number under here. Okay? Cube roots can go into the negative, square roots cannot. Here's question number 5. Determine which graph matches the function f of x is equal to 3 times the square root of x. Okay? Easy enough. Which one shows a square root? This one, because it stops. It does not go into the negatives. Here are your quick checks. I will not give you the answers to these. Compare the functions f of x is equal to x cubed plus 1 and g of x is equal to x plus 1. Which of the following statements is true about the intercepts of the functions? The x and y intercepts are different for each function. Both functions have an x-intercept of negative 1, 0 and a y-intercept of negative 1, 0 and an x-intercept of 0, 1. Both functions have an x-intercept of negative 1, 0 and a y-intercept of 0, 1, and the graphs intersect at 1, 2. The easiest way to do this is to take this formula and this formula, plug them into GeoGebra, and look at the graph. Okay, they never explained how to do this in the lesson. Yay! Quick check question number 2. When comparing linear, quadratic, cubic, and exponential functions, what key feature do all 4 function types share? Then that gives you choices. Go back and look at your table that should be in your notes. Quick check question number 3. Compare the graphs and determine which one could be the graph of a square root function. What does a square root look like? Okay. Use your notes if you need to. Quick check question number 4. Compare the graphs of f of x is equal to the square root of x plus 1 and g of x is equal to the cube root of x plus 1. Which of the following options is true? Both functions are increasing on their domain. Both functions have the same domain of x is greater than 0. Both functions have the same range of negative infinity and infinity. Both functions go through the points negative 1, 0, and 0, 1. Take your time, figure it out, get it right. And this is all based on season 1. My favorite person was Joyce. And I say that Joyce became the best mom in season 1. At least for Will. Angie and I are always laughing at how much she just does not care about Jonathan. Jonathan may as well not exist because, yeah, she has zero concern about him and his safety.